Welcome to breadboarding. In the previous video, we managed to get our 386 CPU here working with all of the control logic down here, and it fixed a couple of issues to do with the 16-bit and 8-bit timing. So that's all working now. Now, during this video, what we're going to do is to add two 32K EEPROMs. Now, these EEPROMs, these are electrically erasable, programmable, read-only memories. These will be having the system BIOS in future videos, but to start with, just going to put some simple test software in here because at the moment we don't have any RAM. That's going to come in a couple of videos time. So what we're going to do for the moment is set up this board and wire it in, and then we're going to go through the assembly language test code that we're going to exercise the system a little bit more. So this is video 17 in the 386 Breadboard PC series, and in this video we're going to be looking at the 16-bit EEPROM, the ROM and the x86 assembly language test program. So in the DeskPro documentation there is a section in here. The Compaq DeskPro 386 system board contains two 16 kilobyte ROMs, one for the odd addresses and one for even. So in fact, it's the way how the system BIOS was configured is to be in 16-bit reads, and in fact the odd bytes and the even bytes were separated between the two ROMs. Now the documentation here, I don't think it's quite correct in that it said that the ROMs are mapped at this F00000. Now in fact that's incorrect, I'm pretty sure, and in fact it would be F00000. So I've got one too many zeros in there, and the reason for that is because this is in the lower 1 megabyte of address space, and in fact because they've got 16K ROMs, so this would be a total of 32K, they actually map the 32K into the F and F8. So it's basically F is a 64K region, F8 is a 32K region. So effectively these two 16K ROMs together make 32K, but it actually appears twice in this address space. So it wouldn't make sense to have this as a 16 megabyte address space and do that. So just go to show that when you're reading the documentation here, you shouldn't always take everything as given, in that this is inconsistent with some of the other data. And then this also references chapter 3 for the regarding dual mapping for the ROM and RAM. And what this is basically about is that the 32-bit memory is much faster than the ROM. It certainly was in the 1980s, so the ROMs would perhaps be 150, 250 nanosecond access time, whereas the RAM was quite a bit faster than that. And in fact, what the DeskPro allowed us to do is that some of the additional memory available was actually put into the top area of the address space. And in fact, what the DeskPro could do is to copy the ROM and put it into RAM, and then write protect the RAM so it couldn't be overwritten. And then this would actually allow the system routines and the BIOS to actually run a lot faster. Now, in order to do this, we need to have the 32-bit memory, so we can't really do that at the moment because we haven't got any RAM at the moment. But what this does actually show is the memory map from the Compaq technical guide, and you can see here that there's actually a space in the memory map for 128K of system ROM from E0000 and F0000 all the way up to FFFFF. So 5 Fs, I believe that would be. So that would be the top of the 1 megabyte address space. And then you can see up here that because the DeskPro only decoded the 16 megabytes of address space, even though the processor were capable of doing 32 bits, which is like 4 gigabytes of RAM in total, only 16 megabytes was actually decoded. And so the top of the memory was this Compaq special memory, which was reserved for shadowing the system ROMs. And when we do this, we should actually be able to see that there may be quite a speed up in some of the BIOS routines when we do this. So to summarise, the original DeskPro 386-16 had two 16K ROMs mapped in the 1 megabyte address space as F0000 and then duplicated at F8000. And note there's one less zero at the end here than on the previous slide. We have one ROM for even bytes, another one for odd bytes. So we're going to need to split the code up. So when we've assembled the code, we're going to need to split it into odd and even bytes. And the jumper switches on the ROM schematic, which I'll show you in a minute, allow for 32K EEPROMs or 32K ROMs. I'm going to be using 32K just because we may need a bit more space, in particular for putting the IDE controller. The XT IDE controller software is going to want to go in the lower area of the ROM space there. So we're going to be using two 32K EEPROMs. That gives us 64K of ROM. And this is going to be mapped from F0000 to FFFF. So this is the top of the 1 megabyte address space. And it will be shadowed into write protected RAM when we've done the 32-bit card, and that will be at FF0000. So this is the top of the 16 megabyte address range. And there is space for another 64K of ROM to go into the E0000 space, which again can be shadowed up to FE0000, and that could be used for basic or other system ROMs. So let's have a look at the original Compaq DeskPro schematic. This is page 10 of the schematic, and what this shows us is the A20 speed up circuit that we're not worrying about. This was to speed up the switching of the A20 address line handling through the keyboard controller. But we've got the PLD here, SROM-A, which actually handles the address decoding for the ROMs. And we can see here that we've got the even and odd ROMs here. So this will be the ones for the BIOS. And then these two here were actually the expansion ones. So the E0000 range. And then there were just two buffers then to take the data from these out onto the main SD0 to SD15 16-bit data bus. So again, the key thing is here is that this is going to be testing our 16-bit data bus and all of the mapping and the translation carried out by the logic, because the ROMs don't go directly to the 32-bit data bus. They go through all of that logic that we've been working on for the last couple of videos. And you'll also notice over here that there are quite a few jumper settings here on the original DeskPro. And so ROMs 1 is the original system ROM and ROMs 2 is the option ROM. So these are the option ROMs here. And then depending on what these jumper settings are, then a 32K device could be enabled. So in the original DeskPro schematic, when I reproduced this, I've actually included these jumper settings. But in the Breadboard PC, I'm actually just going to hardwire this to the 32K devices. So the way how some of these address lines and things are mapped and the enables and things will be based on the 32K device settings in here. If we have a look at the KiCad schematic, so for the moment I've put the EEPROMs over here, so you can see that we've got the two EEPROMs, we've got the two buffers that basically take the ROM data. This is ROM data 0 to ROM data 7, ROM data 8 to ROM data 15, and then put those out onto the 16-bit system data bus. Our PLD here, the SROM-A, this actually uses the bus address latch enable to latch the inputs here. So this is the latchable addresses. So the higher address lines that go up to the whole 16 megabyte address space, so LA17 up to LA23, these are just buffered through from the processor rather than being latched like these other ones. And so these ones were available slightly earlier in the cycles than perhaps these other ones were, and this allowed some of the memory boards and things to do the memory decoding a little bit faster than they would be able to do as if they were actually latched like these ones. The inputs here are the latchable addresses going all the way up to the 16 megabyte of top, and then there's also the SA16, which is just the standard ISA bus address bus here. We can see here that we've got the ROM enable here, and this is also generating the signal, the low enable, that actually controls the output of the read and write signals here. So these two signals here will only be output for addresses in the lower 1 megabyte range. These will be output for all ranges. At the moment, I think we've wired this low, so when we wire this up, we're going to need to worry about that. And there's also an input here for some of the memory refresh logic. Again, we just need to find something that we're going to configure that for. And this also takes inputs for the memory 32. So when the 32-bit memory card is being accessed, takes into account this. And this also generates the output here to set the M16 line to be low, to be active. So when the ROM is being accessed, then this output here will cause the M16 line to be pulled low. So because we've got 16-bit access for the BIOS EEPROM here, then when the EEPROM is accessed, this will actually pull M16 low. We're going to need to go off and wire all that lot up. I've done the chip labels for all of these, and those have been printed out. Going to be using zero insertion for sockets for these, just so that as we pull them out and put them back in again, then we don't damage the chips. And I'm also going to be wiring up some of these address signals between the two chips and some of the control signals between the two chips. I will be using some of the wire wrap using the 0.1 inch pin headers as well, just because it's a bit easier to do in tight space constraints than using lots of DuPont rainbow cables. Now once you've wired these up, we're going to need to program the two EEPROMs here, and I'll just show you the software that we're going to use for that. This is a test ROM assembly language. So this is based on the test RAM that I did in the original Breadboard PC version 2. Now because we haven't done the RAM yet, because it's much more complicated than the original 8-bit micros, this is actually just going to fill the bottom 60K with repeating 0 to 255. So this NASM instructions here basically says repeat this in a loop 240 times, and then just repeat this and output a byte, and then increase the number. And so basically this will fill the bottom 60K of our EEPROM with just ascending bytes. And it just means then that what we then do is to set the data segment to the upper area, so F000, which is the top area where our 64K EEPROM is. Then all it's going to do is to read the value of each byte individually, increase the DI index. When it gets to 60,000, then it will stop, and then so once it's done that, it should then just halt the processor. It's a very simple test, but we can't do much at the moment because until we have RAM, we can't do any sort of stack operations or anything like that. All this is going to do is to show us, can we actually read all the memory addresses, and are we getting the bytes back correctly that we'd expect? And if we actually have a look at the listing output here, you can see that in fact FFF0 is the reset sort of address that the processor comes out of reset. So it's going to actually find this instruction here, and what this actually does is jumps to our test start, and what we've done is defined our test start as being at F000, and all this is actually doing is just doing this sort of test. And you can see up here, these are all the instructions assigning our ascending bytes. So it's probably not that easy to see it here. If we actually have a look in the binary file, so you can see here that we've actually just got ascending bytes going from 0 to F all the way down to FF, and then repeating lots and lots and lots of times. Then when we get to the end, we can see here we've got our reset code here. So this basically is effectively the reset vector or reset address that the processor goes to. And if we just go down to F, we can see here this is our code, our test code that's actually just going through this. So what we should see is when we look in the logic analyzer of this, we should see that it's actually reading these sending values from the ROM for about 60,000 times, and then it should halt. Now in order to split the 64K binary, then the srecord cat utility. So this is something I've used previously for the srecord format. This is a sort of text hex format, came from Motorola, but this instruction here will take our image and split it into the even bytes, and this one will split it into the odd bytes, and then we can actually combine them in using this instruction as well. So in fact, I've assembled it, and I've also split it into the even and odd parts. So this is our binary file, which is 64K. And you can see you've got 00, 01, 02. If we actually look at the even one, we can see that now we've only got 00, 02, 04. If we go down the bottom, you can see that even that with the reset vector here, we've only got the even bytes for the reset. And in fact, if we go, you can see also here that we've got the code that we're using for got the code for the testing there. And similarly, you can see here we've only got the odd bytes. And again, at the end, we've just got a couple of the zeros there from the reset vector. So I'm going to go off and wire all that up. I'll speed it up quite fast, and then we'll plug it into the ISA 16-bit bus, and then we'll have a look and see whether or not we can get this running. Okay, so just going to make a bit of space. I'll just move those out of the way for the moment. Disconnect the logic analyzers and move these over here. And disconnect our dip switch board now because we don't need that anymore. So we're going to have some real software in ROM. Just going to move this across a little bit and move the camera down so we can see a bit more clearly when we're doing this other board. We've got the two 0 insertion 4 sockets. I've got the two 32K EEPROMs. These are 32K times 8 bits, 150 nanoseconds. So they're probably faster than the EEPROMs that existed at the time of DeskPro, in that EEPROMs around that sort of time would probably be about 250 to 450 nanoseconds access time. But compared to our RAM has 55 nanosecond access time. So these are probably a third of the speed of the RAM. So we should certainly see some speed up in performance if we actually shadow the EEPROMs into RAM. I've also got the ATF 16V8B, which is the PLD we want. And there's a couple of 74ALS 541s, which are the buffers to go onto the data bus. So I'm just going to go off camera and stick the labels on the various chips, plug them in, and we'll lay things out, and then we'll start to wire things up. So I've stuck the labels on the chips and plugged them in. I did swap the boards around so that the red power lines are on the top, which is consistent with the schematic. This thing over here is a breadboard buddy. So these are from Hack Modular on Tindy. They're little printed circuit boards that you can just solder couple of pins in there, and the pins are then connected through the circuit board there. So it gives you quite a low resistance connection between all those things. It's certainly a lot neater than putting wires in there. So that's got all of the power rails tied together there. Now, when putting 0 insertion 4 sockets in, it is important to make sure they're spaced out so you can still actually do and undo them like that. I have in the past sort of left myself too little room. And I've already laid them out with the power here, so it makes it a bit easier to see where everything is. You can see, in fact, there's a couple of holes on this side, but in fact, if you look over here, you can see there's a couple of holes on this side as well. Just the orientation of the camera means you can't easily see it. So hopefully that should give us enough space either side to wire everything up. So what I'm going to do is to take these out for the moment and just put the chips in. So I'm just going to put the chips in where the power goes there. Just rest them in there. It's just easier to wire these things up. There we go. I think that's the same as those. So these things, you can see I had to solder more pins on them. One of the ones I managed to solder them in a little bit differently, so you can see that one lot of pins is slightly narrower than the others, but these things mean that when you're unplugging the EEPROMs, reprogramming them, you don't actually bend the pins quite as easily as you would otherwise do. So we've got the plus 5 volts and the right enables also tied to 5 volts here. There's a couple of tied to grounds for some of the enables here, and the rest are just the power signals. We can see those here. So you can see we've got the G2 is tied to ground there, and the right enable is also tied to 5 volts there. So I've wired in all the power pins. So what we're going to need to do first of all is to do all the data lines. So we've got the RD0, RD1, RD2 going all the way up to RD7, and we've got RD8 going all the way up to RD15. So these are going to be white wires, which I tend to use white for data, and so we're just going to wire those up, and then we'll come back and look at the next things we need to wire up. That's the data lines. Now we need to wire in some of the control signals. So we have the ROM enable coming from the PLD here, going to enable here and the enable here. Now, in fact, this chip is in the middle here just because it made it a bit easier to wire things up. So we just need to wire in those signals. And then there's also the ROM output enable needs to be wired into these two output enables here. So now I need to wire in all the address lines. So this is going to be quite messy because you can see here we've got SA1 to SA8, then 13, 15, then over on this side we've got SA11, 12, 10, 9, 14. So it's all a bit of a mix. So what I'm going to do is to bring the SA0 to SA15 connectors in over to the left hand side over here, and then I'm going to use the sort of pin headers and wire wrap cables to tie all these things together. So I've made up a load of pin headers already. So these are going to go against all the address lines up here, the address lines over here. Then over on this side we have a gap, so we have a gap there. And I have checked these will clear the zero insertion force sockets, so we should be okay space-wise there. I'm actually going to bring in the jumper cables for the SA0 to SA7. Going to come in there. SA8 to SA15. Going to come in there. And we're going to put this connector here. This is an 8-way connector. And I've actually got an 11-way connector here. And the reason for that is that in addition to 1 going to 7 there, so we're missing out 0 because we've got 16 bits, not 8 bits. So the SA0 is not relevant when we're dealing with 16 bits. But we need to have the 8, 13 and 15 populated. So what I decided to do is, this is 11 pins. So we've actually got the 8 from SA0 to SA7. We can just wire in SA8 and SA13 and SA15. So this means we just need to now go off and do the wire wrapping, connect SA2 to 7 to 8, 13, 15, all down to here. And then these ones here, we've got 9, 10, 11, 12 and 14 just need to go down to here. So not all of these will have connections. It just seems to be a lot easier. And then we'll use the wire wrap tool to go from there to there and from there down to there. I'm just going to go off and do that. I'm not going to record that on camera because it will take an hour or two to do that. So when we come back, we should have all those things wired up. And then all we're going to need to do then is to worry about the extra control signals that go off to the rest of the board. Okay, so I've made up these wire wrap connectors. So on this side, we've got all of the address pins. So SA14, SA9, SA10, SA12 and SA11, all wired between the two chips here and then wired down to the appropriate pins down here. And on the other side, you've got SA15, SA13 and SA8 wired down to here and then to here, and they come round to this other side over here. So you've got 8 to 15 here and 0 up to 7 there, and then our 8, 13 and 15 are these last three at the end here. So I have tested all of these with the continuity tester to make sure all these pins are connected across the way, so there aren't any loose connections there. I've also plugged in some 8-way DuPont cables, so these are like the individual pins, and then taken the single connectors off and put an 8-way shell on there, so that makes these a lot easier to plug in and out. So this is actually going over to the SD8 to SD15 on the data bus, way over on the other side of the board. We'll have a look at that in a minute. This one is the SD0 to SD7, similar to the one over here. And this one has to go to the latchable address 17, 18, 19, 21, 22 and 23. Then LA20 is a special case that we covered earlier, and that goes off to a different chip. And then the SA16 is also connected there. So in making these connectors up, this end is fairly straightforward. It's just 8-way, but the other ends are going to be a bit more complicated to plug into the various bits of the board. I'm just going to move the camera out, so we need to now start wiring in some of the control signals. There's a number of control signals along here that we'll have a look at in a second that we need to wire in. So just going to go and take a look at those. So you can see here, this is just the to-do list that I work through. So we need to connect the SA0 and SA1 to a 2-way connector, and SA2 to SA7 to a 6-way connector. And similarly for these other ones, so the SA8 and 9 to a 2-way, and the 10 to 15 to a 6-way. And then this other one has a 2-way, and a 3-way, and a 3-way, because of the way how the outputs on the chips are arranged, and because I haven't changed the outputs of the pins really from the standard Compaq DeskPro design. I haven't optimized them yet to work with breadboards. And then we've got the 2 data cables. Now, in fact, these are using 18-inch DuPont cables. So the normal DuPont cables I use go up to about 30 centimeters or 12 inches, but these are some I got from Amazon which go up to 18 inches, which will be needed to do the stretch all the way across the CPU to the far side of the board there. Should also just say that I've connected this board up onto the rest of the breadboard here, and I made these little strip board VariBoard connectors. So the end that goes in over here has just got 2 pins on each of the power rails, and then there's sort of staggered ones here, so alternating rails here and a sort of diagonal. And this just means that we can connect the breadboards together at right angles, and the power will also be connected as well. So you've got one there and one there, so that should keep the board fairly stable. We probably need to shuffle things around when we add all of the bus rails and bus connectors and things, but for the moment this should actually get us going. So you can see here that we've got our leads going all the way over here. So this is the SD8 to SD15, and these are the 18-inch long DuPont cables. Now I did, in my tutorial series, I did actually test out that cables this long, that the signals wouldn't degrade too much. So I'm pretty confident that the reliability of the project won't suffer too much from these. And then this is the lower 8-bit, so this is SD0 to SD7, and then this is our latchable lines, and the latchable lines go over here. So there's 2 blocks of 3 here, and the block of 2 goes into the SA16 and LA20 that comes from this buffer here, which is how the original DeskPro and the PCAT maintain compatibility with old 16-bit software that didn't know about the memory above 1 megabyte. So we just need to now connect up some of the control signals. So we'll have a look at the schematic and wire up each one of those in turn. We're going to do the bus or board address latch enable first of all. This goes from our PLD on our ROM board over to the other side of this chip here, and I think in fact comes down to this output here. So we've got a little BALE label on this chip, so I'm just going to wire that in. Now we're going to do the memory 32. This goes over to U68. Until we add our 32-bit memory card, which will be coming up in another video or two, then this is actually plugged into 5 volts at the moment, so the 32-bit memory option is currently disabled, and this is going to be running primarily in 16-bit mode. And we need the M16E. So what this does is when the ROM is selected, it tells this buffer here, the M16 line is pulled low, and it means then that the control logic down here knows that we're going to be doing 16-bit data accesses. We just need to pull out that cable that's tying that to the power rails for the moment, because now we've got the proper cable in there. So I'll just leave the label in there, the flag in there for the moment, but we probably don't need that going forwards. Now the refresh input won't be used at the moment because we haven't got the dynamic RAM refresh. We are going to need to enable the dynamic RAM refresh even though we're not using any dynamic RAM, we're just using static RAM, because the refresh timing was how the variable speed control in the Compaq DeskPro 386 worked. So this enabled the fast 386 processor to behave more like one of the slower processors if there were games and things like that that were dependent on certain timings from the original PC and PC-AT. So just going to plug that into U31. And finally, we've got the memory read control line. This will go low when we're reading memory or the ROM. So we just need to wire this in down to this buffer down here. Okay, so that is now wired up. Now the only thing we do need to do now is we've got the even and odd ROM chips here, so we're going to need to program in our EEPROM programmer, so I'm just going to go and do that, and then we should be ready to switch everything on. I've still got all the logic analyzers still wired up, so this is why there's lots of cables over everywhere, but these logic analyzers I'll pull back over here once we actually start testing this. So let's take the even ROM out first. I do need to put this in going from the bottom here. And we've got the AT28C256, that's a 32K EEPROM. Just going to read it first of all, just to make sure that it's in properly. If we try and program it when it's in the wrong way around, then it might damage it. Okay, so that's okay, it's read it okay. Now we're just going to load the even part of the ROM here. So the test-rom.bin is the output from our program that we looked at earlier. And this is the even side, and this one is the odd. So just going to choose even for the moment. And we're going to program that. Okay. When we're taking these in out, do need to make sure that things are put in the right way round. And generally pin 1 tend to put up where the lever is. We can see that VCC and red is there. So that should be the right way round. Let's do the other one now. And we're just going to load the odd. We can see here that the bytes at the beginning of the ROM go up into 1, 3, 5, 7. The other one was 0, 2, 4, 6, 8. So the first 60K of the ROM has all of the ascending bytes and things, which the program's just going to read through the ROM ascending. It'll just allow us to check that things are being accessed correctly. We'll just program that and fit that back in. Okay, so that is now wired in. We've still got the logic analyzers set up there, so I'm just going to go off and set up those logic analyzers. Okay, so I've wired up the logic analyzers, everything's been programmed, it's all ready to go, but we're up to about 35 minutes now. So I think what I'll do, I'll break the video now and I'll publish the testing of this a little bit later on in the week. So if you don't want to miss out on future videos, then please hit subscribe. If you found the content interesting, please hit like, just helps to make the videos available to more people. If you'd like to leave comments below, I do try and get back to you within a day or so. Thanks for watching.